So here actually you see a barrier here. And we call this barrier like a built-in potential barrier. VBI, or sometimes we call it VBI. Q times this volume is the barrier height for the energy. So this barrier height is given by this equation. And actually we can derive this in the next slide. This depends on the doping density, Na and Nd. And we can derive this from the next slide. How much is this barrier? So you can see here we have a single Fermi level EF, and then we can look at the distance from the Fermi level to the conduction band edge EC. To the N-type, you know, this is the distance, let's call it A. And then for the P-type here, we have the distance B. So let's look at the N region first. You know, this is what you have done in your homework 1. To get the distance, then you will use this equation. Electron density equals to Nd in the N-type region, and then equals to Nc and the exponential, this Q and this A, which is difference, and then over Kt. So you get the difference A, that is the EC minus EF. So you get this Kt over Q log Nc over Nd. And then you can also get B. Okay. In your homework, typically we ask what is this, right? Because this is P-type. We care about how close the EF to the EV. But still you can get the distance for the EF to the EC. Either use band gap minus this one, or directly you can calculate using the electron's density. Although the electron is a minority carrier in the P-type, you can still use this NP product. Because you know NP product is Ni squared. And then in the P-type region, you know P equals to Na. So you can get N equals to Ni squared divided by Na. And you know Ni squared and Na is given, and you will get the distance for the B, which is EC to the EFP. So you can get the, because this is electron density. Electron density is always determined by how far away the Fermi level to the conduction band edge, which is B in this case. So you get this equation, and you can solve for B, and you can get this one. And then now you have B and A. You know the built-in, this barrier is just a B minus A. So you will get this formula here. And you know when you have the two log term, you have the minus here. Then it's like if you take the log out, then those two terms will be divided. Right? This first one will be divided by the second one if you take the log outside. Then you will eventually get this one. So this barrier height depends on the thermal energy and then natural log Nd Na over Ni squared. And you know Ni squared is a constant. That is intrinsic carrier density, of course, at certain temperature. But then Na, Nd is your doping density. You can say that if you have higher doping, then larger this barrier. I don't require this derivation for you, but if you want to get this airtight. This is the approach. So, any questions? All right. So this is the built-in potential. And let's look at the current components to answer your question. Right? There's diffusion, you said. Yes, there's a diffusion. So this is still again at the equilibrium state because we have a single EF. The applied voltage is 0. That means we have a single EF. So let's look at electron first. So you know electrons are in the conduction band. And this side is N-type. That means you have more electrons. So that means you have many electrons here. And then the p-type, you know electron is a minority. You have few electrons here, but more holes. And then similarly for the N-type, hole is minority, you have less holes. So you look at this, you see more electron here, less electron here. So then the diffusion will happen, right? So diffusion, the electron will diffuse from this side, the N-type to the p-type. Meanwhile, you see here there's a slope in this band, as we reviewed at the very beginning of today's class. Slope in this band means what? Electric field. And then electrons tend to fall down this. Then you will have drift, right? So similarly, this electron will drift to from the p-type to the n-type, and diffusion will make electron diffuse from n-type to the p-type. Similarly, you can argue for the holes. Holes will diffuse from this p-type to n-type. Hole will drift from the n-type to the p-type. Remember, the hole tend to move up, so the drift means move up here. So this is the components of those currents in this PN junction. And then let's look at the equilibrium state. Low bias. Okay, again, this voltage equals to 0. Single Fermi level. This is what we draw from the previous slide. We have more electrons here. However, this electron will follow some distribution in the conduction band. You have more electrons down here. And then, remember, this is energy band diagram. The higher location here, or higher level here, means the energy higher for the electron. So this will follow this Fermi statistics we discussed earlier in lecture 4. This is the distribution of the electron in the conduction band. This is the electron density versus the energy level. So you know there are two factors determine this distribution. One is the density of states. One is the Fermi function, the probability. So at the very, let's say, bottom here, then the probability is high, but then you don't have too many density of states. As you increase the energy, move up, then you have more density of states, but the probability will be low. Because here you can use that Boltzmann approximation already, because your Fermi level is way below. So that means this is an exponential tail here. This is an exponential tail. That means the probability to find the electron with higher energy will exponentially decrease. So this distribution actually is a exponential decay in terms of the number of electrons when you go up. Okay, so then we talk about those electrons tend to diffuse. But here we have a barrier due to this built-in potential. So the electrons down here, they cannot jump over this barrier because they don't have enough energy. It will be reflected back like this. So only the electrons in the top will have higher energy than this barrier, so they can jump over. But the probability to find this kind of electron is exponentially low. So you don't have many, actually, don't have many electrons with such high energy. This is also true because electrons, tend to move down, right? That means most of them will stay to the bottom. But due to the thermal statistics, some of them, few of them, will have high energy like this. But most of them are here. So these electrons at the top will diffuse over this barrier. Meanwhile, here we have the drift from the p side to the n side. So this drift is due to the minority carrier. And then if you have electron at the edge of this depletion region, then it will fall down. And then this electron flow is limited by how many electrons available at this edge. But this number is also small because it depends on how many electrons you have there. But in the p-type, electron is minority, so you don't have many, right? You don't have many. You have very small number of electrons available there. So you have small drift currents, and then you have this small diffusion current. So those two will cancel each other. This is as expected because this is at equilibrium state. Voltage equals to 0, so the net current is 0. Similarly, you can apply this argument to the hole here. Hole tend to move up, right? So most of the hole here in the p-type is here. And then they tend to diffuse, but it will be reflected because of barrier. So only the hole at the very bottom can move over this barrier. And then the hole drift is also due to the minority hole in the n-type. So those two will cancel each other, similarly as the electron. So here the conclusion is no net current, no bias. This is as expected.
So the electric field's presence is because of those charge?
Yeah, exactly. So here we see the slope, right? We say there's an electric field. This is from the band model point of view. But you think the bound model, right? Why do you have the field? Because you have those fixed charge due to the dopant ions, like the arsenic or boron ions. Then you have the electric field. So as we discussed many times before, this band model, essentially are talking about the same physics, but from different perspectives. All right, any questions? So then we will look at what happened when you apply positive voltage. So far, we only talk about the equilibrium state. Now, we are going to apply positive voltage. Again, to make the, let's say, analysis consistent, we assume the n-type is ground. Okay, n-type is ground. And we apply voltage to the p-type. So this positive voltage to the p-type. So what will happen here? you apply external voltage. That means you have external current flow. So you know, from the ground side, the electrons will inject into the device from the electrode. The electrons will inject from the ground. And the electrons will move basically from here and then travel to here and here and here. So when electrons travel to here, what will happen?
Space time.
It looks like you have electrons here, right? That means this depletion region will shrink. Look at this animation one more time. Right? So now you apply external voltage, external charge, like electron go into the device from the ground terminal, and then travel to here. Then this shrink. Similarly, you can think about the positive holes inject from the positive terminal, and then so previously you don't have holes here, now you have holes here, then this shrink as well. So the conclusion here is depletion width decrease with the positive voltage. You see this depletion width decrease. Alright, so this is from the bound model. But later, when you apply larger and larger voltage here, so those electrons travel to here, but then it will diffuse out across this depletion region to the other side. So this side you have more electrons. So these electrons will further diffuse into the p-type. Meanwhile, this hole will also go this way, and they will recombine somewhere here. This hole is a majority carrier in the p-type, and the electron is a minority carrier in the p-type. So they will meet somewhere here and recombine. But from the current point of view, this is continuous. The current can be either carried by electron flow from the right to the left, or by the hole from the left to the right. But the current will be continuous.
So is the takeaway here that electrons are going to be flowing from your N to your P side, which makes current flow the other direction?
Current flow definition, is always in this way.
Right.
But the electrons will travel from here all the way down to here, and then now electron will see a lot of hole. Then they will try to recombine. Right. So once you recombine some holes, that means you need more holes supply from this terminal, from the positive terminal. Right. So hole will go here and the electron will go here.
Right.
And then from the current point of view, you will have continuous current.
Why did the holes not travel to the N side and recombine there?
Yeah, it's the same thing.
They also do?
Yeah, the same thing here. Yeah, so the hole will travel to, some of the hole will travel to here, right? And then electron will travel to here, they will recombine here somewhere.
So there is drift occurring in the N and the P, and then there's a diffusion of the minority carriers.
There is diffusion of the minority carriers and drift of the majority carrier. Yes, yes. Okay, so but it's easier to look at this process from the band model. That's why I prefer the band model. And it's more important for you to understand the band model. So this is the band model at equilibrium. right? So it's just emphasize the Fermi level is flat, single Fermi level. Now we apply, let's say this is ground always as your reference. And then we apply positive voltage. For example, 0.5 volts, positive 0.5 volts to the P side. Then what will happen? Any idea? If you recall what we discussed at the very beginning of today's class, positive voltage to the band means what? Means push down the band. So here we use the N-type as a reference. That means the ground, the right-hand side will stay there, will not move. And then apply positive voltage to the P-type, to the left. That means the left P-type Fermi level will push down, right? So EC, EV will also follow that, will push down by this 0.5 electron volts. So that means this Fermi level will split up, okay? This EFP no longer equals to EFN. The EFP will be lower by 0.5 electron volts. So you see this, after you apply this positive 0.5 volts as an example. So previously this EFN, we assume this N-type doesn't move as a reference. Now this EFP moves down by 0.5 electron volts.
Why did that happen?
This is what we discussed in the last lecture, right? So positive voltage to the band means because positive voltage to the electron means lower potential for the electron.
EC and EV though, but
Everything, because EC, EF, EV, their relative distance will maintain. So those three will move together. So that means here this barrier height will also reduce. This barrier by 0.5. Because everything will reduce here, you see. So this barrier will reduce. That means what? Let's look at this again. So the electron, we just said, you have this kind of distribution, right? Like more down here and then less to the top. But now, since this barrier is reduced, so you will have more electrons that will have higher energy than this barrier. Previously, maybe only this top one. Now you have more electrons can diffuse over this barrier because this barrier is reduced. And on this side, this drift current will not change. Okay, so drift current is determined by how many electrons available at the edge of this depletion region, which is a minority character density, which will not change. So here the barrier reduced, you have more electrons jump over this. So you have electron flow to the left, that means current flow to the right. So this is consistent with this circuit symbol here. Your current is from P-type to the N-type. It doesn't work.